potential energy stuff. So first, when you hear the word potential, and I did this in the other class, it's very simple. If you stand on a chair or on a desk, right, just very easily, not falling, what do you have the potential to do? Fall off, right? Okay. Now, no, I'm just a chair behind me.
The swivel chair.
Swivel chair, I'm going to fall pretty soon.
That could be America's Funniest Home Video.
So,
Howell takes the tumble.
if, it's really funny. I should have put that video up. Next year. So, the reason we call it potential energy, okay, is because right now I have the potential to gain energy in another form. Okay? Again, this is new stuff, not getting ready your test. I have the potential to move or gain energy in another fashion. So if I were to jump off the chair, I'm not going to jump because it might slide out. But if I were to just hop off the chair, on the way down, when you drop or jump off something, what do you start to do? Hello, Sibylla, hello. Yesterday we talked about being distracted. Focus. Now, if I were to jump off the chair, if I were to somehow just leap off an object, I have the potential to gain velocity, right? To pick up my speed on the way down. So whenever you have some sort of a height difference, think about potential energy. Okay? When there's a height difference. So if you're on the top of a building, an object that can fall off has potential energy. Now, once it starts falling and it has speed, then it has potential and kinetic energy. And we'll go into what happens there also. Okay? Hold on, get a hand up.
Wait, so this is like the thing that we always learn with like the top of the roller coaster. It's
Exactly.
potential, and then when it starts
bottom
moving,
is the kinetic.
it's kinetic and potential, and then the bottom's kinetic.
Exactly. It's a roller coaster example. Exactly. Very good.
I don't get that.
Tristan.
Could you explain what potential energy is?
Potential energy means that you are currently not giving off or showing energy like kinetic. You can see that you have energy because you're moving. Potential energy is the idea that you can change energy. So for example, in your pen or pencil, you should use a pencil, but in any pens you see springs, right? Yeah. Springs are a type of potential energy. Because what happens if you push a spring down? What does it want to do?
Bounce back
It
up.
wants to bounce back up, right? There's a potential for it to move or change. So it's a potential energy. For example, what about like when you see say again? Sure, very good. It's on a hill, it has height, and it's angled down, so it's got potential energy, so it'll start to roll down the hill. Very good. That's a great example. Okay? An example from chemistry from last year that you might think about is the bonding. Remember when you have certain bonds between molecules? You have like hydrogen bonds, carbon bonds. Those have potential when you break the bonds. And if you remember, when you break a bond, it releases energy. So you have potential to release energy in a sense. Okay, so think about if you're on top of some height, you have potential to fall. If you compress a spring, you have potential for that spring to expand. If you expand a spring, it wants to contract. Okay, so the things we're going to talk about in this section, today specifically, we're going to talk about potential energy that has to do with height. On Tuesday, we're going to talk about potential energy with springs. Now, potential energy in bonding, like in chemistry, that topic is something that you will see if you study advanced physics or if you go on to like engineering. Like when I studied engineering, we looked at the chemistry behind it and we looked at potential energy in the bond, and when the bond breaks, what happens? How much energy is released? Okay, it's like the valence electrons jumping from one level to the other. When you have an excited electron, when it drops back down, it has to give off energy in the form of light. That's why you see light. Okay, it's got potential to give off energy. Yeah, at some point in time, you'll have a part of the problem where the potential and the kinetic will be balanced. So for example, at the top of this building right here, imagine the object is sitting right at the top, okay? So it starts right here. Now, imagine the object is not moving. What kind of energy does it have? Only potential, okay? And as Helen said a minute ago, like the roller coaster, when the object starts to fall on the way down, at this point in time at level B, it's moving now, right? Because it's falling. So now it has kinetic energy. But it also has potential energy here because it's got some height. Now, what?
Because it has some height to increase in speed, or...
Sure, that's the way to think about it. It has height, which gives it potential to increase its speed further. So right here at the top, it's all potential energy. In the middle, it's got potential energy, and it's got kinetic energy. But at the bottom, once it comes to rest at the ground, or, sorry, right before it's about to hit the ground, not at rest, right before it hits the ground, it's moving, but it's got no height, theoretically. Imagine I drop this pencil, and it's right before it hits the desk. It literally is right beforehand. It's got like no height in a sense. I know it's a very infinitesimally small height, but imagine it's got no height. Infinitesimally? Very, 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 very extremely small.
Infinitesimally.
Infinite?
Microscopic.
Infinite?
Infinite.
Infinite?
Infinite.
Tessimally.
Tessimally.
Infinitesimal.
Infinitesimal.
Yes. So infinitesimally small or large means very, very, very small or very, very large. Like infinite, infinity. So here, right before it hits the ground, like the instant before it hits the ground, it's got no height anymore. So there's no longer any potential. And all the energy is kinetic. And then it'll bounce for a while, it'll come to rest, and then it'll stop moving, and then it'll have no energy.
Potential after B, why?
At the very, 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 very instant before it hits the ground, it has no potential.
Why?
Because potential energy, remember, has to do with the position or the height. And we're going to talk about the formula in a minute, okay? So again, the idea is this. If you have some sort of height above ground level, so imagine the tile floor is ground level. If you stood on this desk, if you stood on this garbage can upside down, you have potential energy because you're giving yourself some height. Okay, so remember, potential energy means height or a spring being compressed or expanded. That's where this comes from. Height is position, shape or condition of the object is to do with springs.
I know this isn't like the same thing, but like it's kind of like on like a graph when you like leave the circle like open up.
As opposed to closed circle?
Yeah, it's supposed to like close.
Like
if
if
you're,
it's not exactly there.
If it's not exactly there, but it's like everything right.
That's what this is,
there.
exactly, yeah, yeah.
So it's like
This
the
would be
same
like having an
thing.
open circle here. Yes, very good. You're like getting closer and closer to the ground, but you're right before you're about to hit
So
the
it's
ground.
not- yeah.
It's like the instant before you hit the ground, or as close as you can get to that open circle on a number line. Yes,
Did you ever have
good analogy.
can it go in the x-axis, like if like you pull back like one of those toy cars that if you pull it back and then it goes?
That's a spring, yes, and you can, absolutely. So if you pull back a car, what it does is it takes a spring and a little gear system, and it takes a spring and it compresses it. And then once you let it go, the spring wants to expand, which causes the wheels to turn, which propels it forward.
So we just fill in the x for where the y is.
Well, no. Let me go back. Hold on one sec, Tom. This has to do with height only. We're going to talk about springs on Tuesday, different formula.
Oh, okay.
Okay? This is this right here. Gravitational potential energy, meaning the height. Okay? That's what we're going to look at today. That's what we're going to look at today. Again, if you have height, you have potential energy. That's what you have to always think about. And by having height, it doesn't mean like you have a height. Everybody has height. But I mean if you have height above the ground of where you're standing. So if you're standing on some sort of an object or something that moves you upward, you have height, you have potential energy. What does M stand for? Mass. Everybody, what is G?
Gravity.
What is Y?
Displacement.
Yeah, your vertical displacement, or in this case, height. Very good. So let's say that at level A, your height was 10, at level B it was 5, and at the ground level it's 0. Now, does it make sense if you plug in the formula? Look, at the ground, your height is 0, isn't it? So you plug in a 0 here, what do you get? So your potential energy is 0. It's all kinetic. Now, at the top, you have a height of 10. So you would plug in a 10 for Y. At the middle, you have a height of 5. You plug in a 5 for Y. So what you can say, if you have half the height, like this is half the height here, you have half the potential energy. So if I start at the desk at 3 meters, and somehow I have a step ladder or a step stool here at 1.5 meters, and I step down, now I've got half the potential energy. And then I go to the ground, and now I've got 0 potential energy. So no.
So if you're trying to find like y or something, you would do like 10 equals n, like whatever n is.
Well, 10 is the distance. I should specify my units. 10 is the Y value. If you were trying to find the Y value, you would need to know what the energy is and M and G and stuff. We're going to get more into that when we look on Tuesday and then after Thanksgiving break. Yeah.
Potential energy.
Again, right? It's like the second time.
This is like.
Sorry.
They look exactly.
I wouldn't say,
Real bad.
but we're recorded right
Chaz
now.
and
So.
Chaz and Tristan, I mix up your names, and then Hannah and Helen.
I don't know why.
Those
Well,
are your only
that's
names.
just a racist joke.
Oh, you know, I know that, guys. I know that.
This is the.
He's potential energy doesn't have to do with work.
It's not going to be, yeah, like we did the work kinetic energy theorem. No, it's not going to be a work potential energy theorem.
Okay, but then what about like potential energy and kinetic energy?
That's what we're talking about. That's conservation of energy, and we're going to talk about that after Thanksgiving break.
Okay.
Okay? I saw another hand besides Dylan's a minute ago. No? We're good? All right. Let's look at an example. Okay, let's take a look at an example.
Get mad curls.
Take a minute to write it down, please, before we begin. Steph, when are you going to get those glasses? Why not?
Can't be.
It's hurting your eyes, you know, right?
Yeah, I know. I'm gonna get wrinkles too.
Oh, besides the wrinkles, your vision gets worse if you don't correct it, you know.
No, but it gets worse if you do.
Yeah, that happened to my
But-
grandma. Her vision
Your vision gets so much worse when you wear glasses because your eyes get lazy.
My life
No,
Yes,
not
they
at
do.
all. Not at all.
Yeah, it does.
That doesn't work that way. Talk
Yes,
to your
it does.
doctor. I'm
Yes, it
100% sure of it.
Helen, who told you that?
It's not true at all. You want to think that, it's not true. If you don't wear glasses and you strain your eyes, your vision can get
No,
worse.
but doesn't that make sense?
People, I can see what you're saying,
I
I'm sure.
wear contacts.
Because your eyes aren't working hard enough anymore. But
Yeah.
that's not the way it works.
No, but I wear contacts. I guess
It
this
has
is
to
just.
do with the.
Is it just because I'm still growing?
We're going to
Every
learn.
time I go to the eye doctor, I can't
It's because
see.
you're growing. We're going to learn about how the way it works. You have rays, light rays that come in on a focal point. If they're not on the right focal point, if they're too far, you're nearsighted. If they're too close, you're farsighted. And it has to do with the angle of the rays coming in. So as your eyes adapt their shape and the cornea itself changes size, you're going to see the light ray changes its location. So over time, your eyes change. That's only because you're growing.
I'm
Nothing to
really
do with
excited to
work.
learn about this.
Strain it will hurt you. You also get, Steph, you ever get headaches from shooting?
What?
You ever get headaches from
All
shooting?
the time.
Yeah, my younger brother never wore glasses, and he had astigmatism.
Oh, the hot
He
one?
would always do this. He'd always go like this. And he would strain so bad, he would come home with headaches. I'm telling him, like, just get glasses or contacts. I don't know. What is astigmatism for an eye?
It's just like your.
Yeah, look at his eyes.
I kind of got it. It's when your retina's really slanted, so your
Wait,
eyes
what is
say astigmatism, which is why like mine shakes so much.
Ah, interesting.
Because your pupils-
Wait, your eye shape?
I wasn't even noticing that, to be honest with you.
That girl in
I can see
Do you feel bad?
That's interesting.
Does it work out?
Are we done copying?
One of mine, they shake.
Can I hear an subscription again?
No.
I know the ground talking about nose and box Yeah, I would do the sum of the forces equals 0 in this because it's stationary. And think about this is -1, this is acting negative x, this is acting y. I'll go over more than one, but now yeah, that's a tough question. Alright, so we've got a 40-kilogram object, alright? It's raised from the bottom of a well.
Let's draw a box.
So, let's draw a box. Here's the object.
FBD.
Okay, it's being raised upward from the bottom of a well, so its motion is upward. The depth of the well is 25 meters, and the object is raised 3 meters above ground level. Again, the depth of the well is 25 meters, and the object is raised 3 meters above ground level. Determine the change of potential energy in the object. Start us off, Tristan.
So it's 25 meters down, right?
So here's the well. Okay.
Okay.
Here's the object at the bottom.
0.
Okay, so we'll call this the 0 level. That works for me. You can call whatever you want the 0 level. That works. Now, where's the object going to? To here?
Just above ground level.
Okay, so then, see that's where you have to be careful here, Tristan. If we call that 0 as ground level, you got to be careful with our problem. Call this the 0 level. It doesn't matter at all, and I'll explain. So now it's 3 meters above, so I should draw it somewhere up here, maybe? That work? So let's do this now. That clear? All right. So that's our diagram for this problem. That's our diagram. Now, The problem that a lot of students have here is they say, well, what is this height here? Isn't this negative 25 and this is positive 3? Just remember this. Y represents the displacement, correct? Displacement. Your formula in your book uses mgh. I don't like that at all. I like mgy because in my mind, all I know is this. How far has this object moved overall?
28.
28 meters, right? It's 28 meters. It moved up 25 and then up 3. So I could say that the y value is 28 meters. And that will make the problem a lot easier. Instead of thinking like, all right, well, this is negative potential energy, this is positive, I have to subtract and add. It's a lot more work. I'm trying to show you guys the easier way. So think about how far has the object moved vertically to find the change in potential energy. If it moves up, it gains potential energy. If it moves down, it loses potential energy. Okay? So keep that in mind. So go.
So like when you're putting something down or like, I don't know.
When you're lowering it,
Yeah, that's going negative.
correct. It's losing potential energy. So imagine if the object started here with a certain amount of potential energy and dropped all the way out to here. Then you would get a negative value because you're going down in the downward direction. 3.
Gravity, 921.
Yes. Now, for these problems, we're going to use 9.81 again, not negative 9.81. The negative 9.81 only was used when we did projectile motion. Okay? So let's write our formula here. Potential energy equals mgy.
Wait, that like confuses me though. Why did we used to use negative instead of like what's the
Because motion with velocity has to do with moving down or up. Whereas here, we're looking at the y direction, or this y here is going down or up. For example, here, this y is moving up 28 meters, right? So I'm going to put a positive 28 in there. If I put a negative 9.81 for g, now I'm going to get a negative answer for energy change. But I know that I gained height, so it's got to be a positive answer.
yeah.
So if you want to think about it as just logically, it will make sense, your answer.
So,
Okay?
question, so if it's going downwards,
Y is negative,
yeah, oh, y would be negative?
which causes it to be a negative change in energy.
Oh, so g what is g
G is always going to be positive here, okay? G is going to be positive. The Y is going to indicate whether I get a negative or positive energy. Okay? Hunter, you sure? Okay. What was the mass of this again?
20, 40, 40, 40, 20. Really? Those stuff? Okay. No.
Be nice, ladies.
We're joking. We just sit around a lot.
I know you do, but sometimes it's hard to tell the difference.
It's kind of a bully.
40 times 9.81 times 28. What do we get, Emmett?
10,987.2.
What are my units of energy or work? Joules. Good.
Oh,
Like that.
lost how we got there.
And joules.
So we don't use negative 9.81. We always use
When we're doing
positive.
energy methods and work methods, we're always going to use the positive 9.81.
And for
forces, same thing.
displacement, we do, if it was dropping down 28 meters, we would put the negative there. So our answer would be negative.
Yes.
Okay.
We're going to do an example of that in a minute, okay? Where an object moves downward instead of upward. Any questions on this one overall? One more example, then we'll go over a quick review of the text. One more example.
Wait, no, wait. I was copying the answer.
40 times 9.81.
1097.2.
Joules.
Camilla, you're so slow.
That was a form of bullying.
Okay. There's some data involved.
All right, so we have an object starting at the top of an inclined plane. Its mass is 5 kilograms. The inclined plane has a length of 10 meters. The angle for the inclined plane is going to be 30 degrees. Or let's say 35 degrees to make it tougher. Because 30 degrees is an easy
Give
angle.
us a complicated figure.
Now, here's the hard part of this problem. And don't answer. Think about it. So nobody talk, just think. If you wanted to figure out, again, you're thinking, you're not talking. If you wanted to figure out the change in potential energy from the top of the ramp to the bottom of the ramp, and I simply use my formula, we know M is 5, we know G, The question becomes, what is y? Think about it for a second. Think about what you think is y, and I'm going to give you 3 options. Okay? I'm going to give you 3 options. Okay, so raise your hand when you think you agree with one of the
Like
options.
you name them all first?
Okay? Sure, I'll name them all first, and you pick. Either y is 10, less than 10, or greater than 10. Okay? So hands for y equals 10. Good. Y is greater than 10. Y is less than 10. Okay, it's
Oh, no,
less
it's
than.
yeah.
It is less than, all right. Let's go over this now. What is the y value always? The vertical what?
Displacement.
Displacement. So really the vertical displacement is from top to bottom. It's the change in the height. I don't care about the x displacement. Isn't this a horizontal displacement? Wouldn't that be the x component? This would be the x component of the movement. This would be the y component of the movement. And I want the y value. So how do I find the y value?
Wait, I thought, like my first thought was that we would do like the two sides, the x and y.
We could, but we
You
don't
could
need
do
to
it like
yet.
that, right? Like the,
Yeah,
We
the
could,
X, the
we
Y,
could.
and then
But there's no need for the x, because we're only looking at the y direction here.
Do like the SOHCAHTOA.
Yeah, use like SOHCAHTOA. What was the y component always? What do you use? Sine or cosine?
sine.
Sine. Remember, it's alphabetical. X, y, cosine, sine. Very good, Erica. Okay, just remember the order alphabetical. That's it.
Someone's feeling hot.
So, here. The value of y is 10 times the sine of 35 degrees. Okay? That's the key here. The key is to remember that the change in potential energy only represents a vertical change. So if something moves at an angle, you need to figure out what is its vertical change by looking at the sine of the angle that is with the ground. Remember, the angle we need is always here. If you are given this angle right here, you need to figure out what this angle is down here. Remember, you're always using the angle between the actual motion and the horizontal.
So whenever we have something that's diagonal and it's not exactly, well, it's not exactly vertical or horizontal, we have to multiply that number times sine or cosine of the.
If you're looking for potential energy, sine. If you had like a force problem and it was at an angle, to get the x, you have to multiply by cosine of theta. To get the y, you have to multiply by sine of theta. Okay? Always, always, always.
Now it's always sine.
Because we're looking at potential energy, which is vertical motion, therefore it's sine. Okay, that's the reason this is going on. So let's go ahead and plug in. PE equals 5, 9.81 times 10 sine 35. Alright? Now, what do we get for this? Chelsea. 281.3. What are my units?
Joules. Joules. 281.34.
Let's just say 281 for now. And you know, we're rounding differently, people? Is that what's going on here? Did you round at all, Chelsea? Eric,
I
did
got
you
the
round?
same as Chelsea.
That's right, you rounded. Don't round. Okay? Chelsea, 281 point? Thank you. Well, maybe you both rounded. Plug in literally your calculator, these 3, just like that. If you rounded the cosine of the sine of 35 and then did it, you're going to get a mistake. You're going to get a rounding error. You never want to round until the very last step. That's why we always solve algebraically and then put our numbers in. Okay? Any questions on this? Going once, twice, all? Thanks. All right, let's take a look at test topics. Now, we have four. Second quarter. Monday. Well, what else is due on Monday, people? Thank you. Now, remind me to show you something on Moodle before the end of the period. Remind me to show you something on Moodle before the end of the period. All right.
Is it Scarlet Takes a Tumble?
No, it's not. Why would that be on Moodle?
It's definitely like, wait,
Energy of Scarlet before she falls, and then the kinetic energy, and then.
On rafting energy? object. Okay? And the weight, you're going to be given that formula. You guys need to really stop talking back there. The second thing we're looking at here, after the weight, was the normal force. Okay? Remember, the normal force does not have a given equation. It depends on the scenario. Okay? Yes, we need to keep up. I can't stop right now if you guys want to hear this. We will run out of time. We will not go over everything. The third thing is friction. Okay, remembering there are two types of friction, static and kinetic. Static is stationary, kinetic is moving. Static friction is always bigger than kinetic friction. Again, remember, in the US, the static coefficient is greater than or equal to the kinetic. We've only seen greater than, we haven't seen equal to. Sometimes they can be equal, but remember generically that it's bigger. Okay? The formula you'll be given, so I'm giving you formulas over here, by the way, so you can have an idea on the test of what formulas you'll be given. The formula given for this will be the following. And F equals mu F n, the one you've seen many, many times yet.
Is normal friction all the time, or
Is normal? This is the normal force, this is the friction force.
where's the?
Does anyone have a pencil to show
Okay, yeah,
another
that's
person?
right. Is there
Yeah.
like
Have we do a
a
pencil?
equation for that?
I have
You have to figure it out based on the free-body diagram.
Oh, I
Now, after friction, we went on before 4 and looked at objects being moved at an angle. So force is applied like a sled. If a sled is on the ground, hint. If a sled is on the ground, you're pulling on it, it's at an angle. Okay?
Uh-oh, we got
So-
a test problem.
Objects moving at an angle. In, or pull, let's say pull at an angle.
Wait, you'll tell us that he's pulling up though, right?
Of course,
It's not
of
like
course.
lying down.
It'll say like the person is pulling at a 30-degree angle or so forth. The last topic was inclined planes.
Mr. Howell, for the one that's being pulled at an angle, you only use cosine, right?
No,
Did
I
we say
mean,
that? No?
that's for work. You're thinking of work.
Oh, okay, okay.
We'll talk about that with work. But forces, you have an x and y component. You use x, cosine, and sine. Okay? So, these are the 5 things from section 4.4. This will be the bulk of your test. Okay? This will be the bulk of your test. The only thing that was on the video that you should have watched was inclined planes. Everything before that we went over in class. So look at your notes in class for the first 4 topics. And then the last thing was from the video you were supposed to take notes on. Now, the thing I want to point out on Moodle is a thing to do with 4.4. That's why I'm saying that. So remind me that at the end. Chess.
I was just wondering, is the multiple choice gonna be based on the stuff in the book, or just?
Multiple choice can be things like, knowing that static is bigger than kinetic. Or knowing, for example, that the work done by an object is 0 if there's no motion. Like certain things like that, theoretical questions.
Trick
Okay?
questions, basically.
Not trick questions, but questions to make you
Little,
think.
little tidbits.
Tom.
So are we gonna, I don't know if you're saying ready yet, but are we
This
gonna
pencil's
use the
so
formula with
soft.
like cosine and sine yet? For the objects at an angle, are you gonna get it? You're not gonna use it?
That you should know that if you want the x component, it's cosine. If you want the y component, it's sine.
Okay.
That's all you do there.
So,
I would recommend looking over your notes on this topic if you're confused on it, okay? Because we did a good example there that is good for your test. Look. All right, section 5.1.
Oh my god, no.
What was section 5.1 called, people? What was it? Work.
Work.
Formula for work.
Thank you. No, you got the pencil all
Now.
over my thing. Wait,
Remember, we did problems
pencil shirt.
where we found the work done by a force being applied, and we also found the work done by friction. If you want to write a little jot or a little note down, the work done by friction is always negative, because that's where you use the cosine of that 180 value, which is -1. So remember, if I pull on an object and I pull and help its motion, the work done is positive. If the friction is slowing it down, the work done is negative. And the work done by friction is negative, always.
Wait, I don't get that.
Object's motion is this way, friction pushes it this way. What's the angle made between my arms? 180. The cosine of 180 is -1. Cosine of 180 is -1. Therefore, whenever it's friction, it's going to be a negative answer. If they're both going that way, theta is 0.
Pulling it, yeah.
Remember, people, you also have to be able to find work done at an angle. So what if the angle is 30 degrees now? We did an example of that in class. You might want to look at that also. Please look at your homework from 5.1 as well. 5-1 was just work. 5-2.
Cos beta x.
5-2 is kinetic energy, and then the work kinetic energy theorem. Okay? Now, kinetic energy formula given. Okay? The work formula, though, is going to look a little different, like I told you. All you're going to be told is the following. Okay? But you can come up with the formula because you know what work is from up here. F cosine theta, plug that in for W. You know what delta means. It means final minus initial. And kinetic energy is also defined. So let's go ahead and write our formula. Now, I'm going to write it in red. Because this formula I'm about to write, you're not given. You're not given. You're not going to be given. The one I'm about to write. Okay, work is F cos theta, absolute value x. So I can plug that in right here. And that comes from my work formula that is given. Okay? Delta KE is KEF minus KEI. This here is really KEF minus KEI. So if I want kinetic energy final, I just write down my kinetic energy formula. But I put a little F here for final. So it's 1/2 mVF squared minus 1/2 mVI squared. So this formula here, boxed in, is not given, but you should be able to come up with that formula if you need to use the word kinetic energy theorem.
Is that another little hint?
Yeah, I mean, I can tell you now that, I'll tell you right now, for math problems, if you want to know, you're going to definitely have a problem with an inclined plane. Guaranteed. You're going to have a problem with a force applied at an angle. You're going to have a problem where you need to do work, or calculate the work. You have a problem with the work kinetic energy theorem. I guarantee you those 4 will be your mathematical problems.
Wait, what's the
Okay? Again, inclined plane, force at an angle. So applying a force on an object at an angle like the
What's
sled.
that under? Is that object?
Or objects pulled at an angle. You'll have a problem from a work topic, a work problem, and you'll have a kinetic energy work theorem problem. Okay?
Oh, wait, so
It'll be 2 from 4, 1 from here, 1 from
I have
here.
a question.
That's the math problems, I'll tell you.
So work to kinetic energy, what would that include? Like, what are we trying to find?
Remember what we did yesterday in
I
class?
remember, but like, I don't know, I just need a refresher-ish.
You're going to have to find, like, imagine you
Guys,
have,
like the thousands of replacements.
imagine you have the force being applied, and you know the initial velocity is 0, it's at rest, and it speeds up to 10 meters per second. Find how long it takes, how far the distance, soft rest.
Okay.
And that kind of stuff. But remember, people,
It's fine.
look how many variables are here. There are 7 different variables in this equation. So, for this problem here, you can calculate any of them. So I might give you F, X, theta, M, VF, and you need to find VI. Or maybe you'll get everything except for M. You have to find M, and so forth. So there's a lot of types of problems you can get here. Okay? So go.
Oh, can you give us the variables that we plug in?
I'm sorry?
Can you give us the variables that we have to plug in for the kind of
What's that mean?
like the mg equals blah blah blah.
M is math.
No, she means like you know how like f equals
Fn equals mg.
Yeah.
I know.
like fg equals mg and then like how you have to.
You're given, look, everything in green you're given, and that blue. So you're going to be given this, you're going to be given this over here, you're going to be given the work formula and the kinetic energy formula. That's it. Okay? Now remember, Fn is not always mg. It's only when something is balanced and it's on a horizontal surface and it's not moving with an acceleration. You have to come up with all those things. Okay? So it's not always Fn equals mg. And you can see that if you look at your inclined plane examples.
Wait, is this it? Is that
Yeah, that's it. That's all topics. Now, Moodle.
Moodle.
Show us something on Moodle. Wait, our problem set 4 is test, right?
I'm sorry?
Problem set 4 is for the test, not 3.
Yeah, the one we.
Problem set 4, the one you're doing now, is on the test. Absolutely. And then homework from 5.1 and 5.2. All right, so on Moodle.
Oh, do you have our problem set? Or could the users in the last 5 minutes from her mouth?
That's what I'm working on still. Yeah. All right, so take a look here. Watch. Your topics from this test, okay? Your topics from this test are under documents and handouts. I put 5-3 homework, let's just say 5-2. It's going to say 5-2. We'll tell you in a minute. The homework solutions. Remember the ones that we did yesterday with the work kinetic energy theorem? There's a document that shows all the work there, and also the topics that I just went over. In addition, this is what I want you to really look at too. This will help you not only on your problem set tomorrow. Remember tomorrow, bring in your problem sets, either your textbook or the photocopy I gave you. This here is a sample solution of a bunch of different problems. So if I can actually click on it.
You could what on it?
Click on it.
Oh.
Now, what you'll see is, here's what the document looks like. It's a bunch of different problems from a different worksheet. Okay, and they give you the answers in parentheses. Now, there's 11 problems total. Then after that, you'll see, here's all my solutions with free body diagrams and how to go through every problem. So this might really help you. Look, object at an angle. Watch, object at an angle. Go further. Inclined plane problems. Inclined plane. Okay? So you might use this for 4-4. You don't have to do that. And for your test to study. I appreciate it, but you don't have to do that. Again, okay? It will help you. It will really help you. Now, one thing to note. Number three, listen, number 3, you're asked to find theta, and you need to use what's called the cosine inverse, which we haven't done. It's a topic in Algebra 2. You might have seen it in your old school, yeah, I remember we talked about it. So if you know it, that's fine, but if you don't want to look at number 3, you might want to just ignore number 3, okay? Just to give you a little heads up, I wasn't going to delete it from the document, but you don't have to do number 3. It might confuse you more, okay? See? I did already. If you look at the description, look down here.
Checkmate.
Feel free to ignore problem 3 since it asks you to solve for data, blah, blah, blah. Okay, it's right here.
There was this problem on the top.
Okay.
Do we have any homework?
No.